Good day, everyone. And once again, we are back together. So we're looking at the Doppler effect this time around. I saw this interesting question from Gauteng Prelim. So I just thought I would just discuss it with you. All right, so if you haven't subscribed, please just make sure you're part of the family. All right, and let's get right into the question, right? So they say grade 12 learners conduct an investigation to verify the speed of a race car using the Doppler effect. A race car driving around the race course at a constant speed emits a single frequency of 200 hertz. They say a learner standing on the final straight records the sound using a cell phone. Right, they says the car approaches him and after passing him, right? So it means that we're going to have two records here. So he's going to record the speed, or rather the frequency of the sound when the car is coming towards him, as well as the speed of the car once it has passed him, right? So they say for this investigation, write down the following: a dependent variable. So remember, when we talk about a dependent variable, right? When it in the Doppler effect, the frequency, the perceived frequency, depends in this case on the speed of the source, right? So in this case, we're going to say our dependent variable in this particular scenario is going to be the speed, no, rather the frequency, sorry. So this would be the frequency, or let's say the perceived frequency, or you can say the frequency of the listener, whatever the case may be, okay? Let's say the perceived frequency. Yeah. Okay, so that would be the perceived frequency, or you can say the frequency of the listener, if you want to. Either way, it all means the same thing. Right, so the next one, they say to us, we're looking for the controlled variable. So for our controlled variable, so remember, this all has to happen in one medium. Okay, so if that medium is air, the speed of sound in air has to be the same, right? The speed of sound, they did say it's air, right? That 340. Okay, actually so the speed of sound in air has to be the same, right? Okay, so the next question, they say a suitable investigative question for this experiment. Now, ladies and gents, I want you to always keep in mind that for the investigative question, you always need to make it such that it probes the relationship between the independent variable. Now, what would be the independent variable here? What are we changing? It would be the speed of, or the positioning of the car and the speed of the car. And as the speed changes, in this case, obviously the frequency would also change, right? So and by the way, it also needs to be an open question. So it means you can't ask a question that can be answered with a yes or no, right? So please keep that in mind. So in this case, I said my independent variable would be the speed of the car, all right, or the relative speed of the car, whatever you want to call it. And then the dependent variable would be the frequency, obviously, of the listener, the perceived frequency. So you can say, well, how will the speed, or you can say the relative speed of the car, let me rather use relative speed in this case. How would the relative speed, okay, please don't mind my ugly handwriting right now. How will the relative speed of the car, and in this case, relative to whom? To the listener, right? Relative speed of the car of the race car, okay, affect, all right, the perceived frequency of the listener. Okay, of the listener. Okay, right. Or you can say the detected frequency, or in this case, you can even say what is the relationship between the speed of the car as well as the oh, and by the way, here's an important point, please. It's an investigative question, so there has to be a question mark at the end. Please, once you don't put a question mark, note that you are going to lose marks, because at the end of the day, it needs to be a question, right? Now, this is the question I wanted to come to, because it gives the most, eh? They say to us, when playing back the sound recorded on the cell phone in the presence of an oscilloscope, the difference in frequency of 67.15 hertz was registered. They say use the information above to calculate the speed of the race car. Take the speed of sound in air as 340. Honestly speaking, when I did this question, it was really, really maths intensive. I'm not too sure even the mark allocation, if they actually really, really thought about it. So let's think about it. So there are two scenarios. So the first scenario would be the one where the car is coming towards the listener who's carrying that cell phone. Okay, so in this case, we know here's the car coming, so we know the perceived frequency must be greater than the frequency of the source, right? So I'm going to say, well, this is going to be FL is equal to, please write down the original formula first. So that's VL all over V plus minus VS, okay, times FS, right? So what we're going to do now is just simply say, all right, so the frequency of the listener, okay, let's say frequency of the listener 1, okay, that's going to be 340, but you remember the velocity of the listener is 0 this time around, right? But we want this to be an improper fraction because we want this to be greater. If you don't understand what I'm talking about, please watch our full video on the Doppler effect. Right, so that's 340 minus Vs times the frequency of the source in this case, which was 200. Okay, so that was our first, formula. You can say this is going to be, so if you look at this, that's 340 times 200. So I'm just trying to get it to be as neat as possible. So that would be 68,000 divided by 340. I don't know if I should be doing that, hey? 340 minus Vs. Okay, let's call that equation 1, as we said. Okay. So then for the next one, this is when now the car is moving away from the listener. Okay, so there's my very handsome friend there. Okay, so the car is moving away, so I know that the perceived frequency would be less than the one for the source, right? So in this case I would have, okay, it would be exactly the same thing. Now it's going to be 340 divided by 340 plus Vs times 200. Okay, so that means I would have that would be again 68,000 over 340 plus Vs. Now remember what they said to us. They said the difference between the two frequencies. Okay, so let that be equation 2. So the difference between the two frequencies is equal to 67.15. I think that's what they gave us, right? 67.15 hertz. So in this case, it means that frequency 1, right, which means this one here, remember it's the one that's greater, minus the second frequency would be actually equal to 67.15. So you've got 68,000 over 340 plus, minus Vs. Okay, so that's minus Vs, minus 68,000 over 340 plus Vs, which is equal to 67.15, right? So what we're going to have to do there is just try to deal with the mathematics. Now, if you remember, when you're dealing with fractions, you're going to have, okay, let me just make some space there. We're going to have, in this case, the LCD, right? So our LCD is going to be the product of the two. So that's 340 plus Vs and 340 minus Vs, right? But now I'll say LCD divided by denominator multiplied by numerator. The ones with the minuses will actually cancel, and I'll have 68,000 into 340 plus Vs in the first one, minus 68,000, okay, into 340 minus Vs. Now, ladies and gents, because this is not a maths session, I'm not really explaining as much as I should, but just remember, when you do fractions, right, you always say LCD divided by the denominator in the first fraction, right? So you see that this and that would cancel, and you'd be left with 340 plus Vs. But then you multiply that into the numerator, and that's why we have that. And the same thing is true for the other side, right? So now, what do we have? So if I take, of course, if I multiply inside the bracket, I've got 68,000 times 340 plus 68,000 Vs, right? 68,000 Vs, sorry about that, minus, okay, 68,000 times 340. Right, now remember, negative times a negative is a positive, so that would be 68,000 Vs, and this is still equal to 67.15. Sorry for squeezing that in there. Okay, and of course, what's our denominator? We've got 340 squares. This is the difference of two squares, right? So I'm going to have 340 squared minus Vs squared. Okay, right. If you notice, this and that would cancel. And that's why I was saying this question is quite maths intensive. I'm not too sure when they made the mark allocation if they really considered this. So that's 68,000 plus another 68,000 Vs. Let me say times 2. So that would be that 68,000 there plus that 68,000. So that gave us 136,000 Vs. Okay, and now remember, this is over 1, so I can cross multiply, right? Okay, so this is equal to 67.15 into 340 squared minus Vs squared. Okay, so now I see I'm going to have a quadratic formula. Okay, I'm going to be just quick about this. If I take that, that's going to be 67.15 Vs squared if I bring it over to the left hand side. Okay, and then I'll have plus 136,000 Vs, okay, which is equal to in fact, no, let me rather also bring that to the other side. So that would be minus 67.15 Vs squared, right? Sorry, not Vs, 340 squared, sorry about that. So I'm multiplying that by that now. So that's multiplied by 340 squared, and this is equal to 0. Now, what you can obviously do is divide everything by 67.15. Okay, that cancels. So let's see, 136,000 divided by 67. Okay, so let's say divided by 67.15. Oh gosh, I get that ugly thing there. Of course, it's going to affect our answer. So I've got Vs squared plus 2025.32 Vs plus, oh sorry, that's minus 340 squared, which is equal to 0. Now, ladies and gents, of course, I'm not too sure that this is all worth it. But of course, we're going to now use the quadratic formula. You see what I mean about it being maths intensive, right? So that's going to be minus b minus 2025.32, okay, plus minus the square root of b squared minus 4ac. So that would be 2025.32 squared minus 4 times our a is 1, our c is 340 squared. Okay, yeah, so just be careful of that. So that's negative 340, not all squared, but that's negative 340 squared. Okay, this pencil of mine sometimes just misbehaves. Okay, so that's minus 340 squared. Okay, right, and all of this is divided by 2 times a, which is obviously our a value is 1, right? So if you look at that, so I'm going to take the first one. Let's see, the other one is going to give me a negative answer, so I'll just take with the plus, right? So that's negative 2025.32, okay, plus the square root of 2025.32 squared, right? Now remember, negative times a negative would be a positive, so I'm just going to make that positive, plus 4 times 340 squared, okay, and gives me that answer there, okay, and all of that divided by 2, okay, and you'll see that our answer is 55 point, so it means the speed is 55.55, okay, meters per second. As I said, ladies and gents, I'm not too sure if this was all worth it, but nonetheless, it is what it is. All right. Right, so let's move on to the next one. They say the spectrum of light from most stars rather contains line corresponding to helium gas. Okay, diagram A shows helium gas, helium spectrum as observed in the laboratory. So this is on Earth, right? And then diagram B shows helium spectrum of light from a distant star. Right, so let's first of all notice or observe something. What do you notice? So the line spectra, okay, in this case that would be our our emission spectrum, right? So you would see that these lines are now somewhat moved to the left hand side, right? Sorry, to the right hand side. So notice that my wavelength is actually increasing, going that way. Okay, so remember, an increase in wavelength, right, means that it's a decrease in frequency, right? So it means that when I look at the distant star, my frequency actually decreases, right? Why? Because I'm moving towards greater wavelength, right? If you notice, first of all, if you just look at that 500 line there, the lines were just between the 500, right, in the first scenario. But now what happens? the lines are now moved slightly to the right where there is a higher frequency, in this case higher wavelength, so it means lower frequency, right? So now what is that showing us, by the way? Remember, in the Doppler effect, it simply means that when we are moving towards the lower frequency, it means that something is moving away, right? So in this case, they're asking, is the distant star moving away or towards the Earth? So it would be away in that case. So that would definitely be away, right? So the perceived frequency from the distant star, okay, from the distant star, okay, is moving towards the higher frequency, the higher wavelength, moving towards a higher wavelength. Okay, or you can say the spectrum, okay, the absorption, the emission spectrum of the distant star is moving towards the higher wavelength, okay, therefore the frequency decreases, okay, the perceived frequency decreases. Now, ladies and gents, I'm not saying this is the Bible, in that you need to write it exactly as I do. You'll find a way to express it, but nonetheless it should be somewhat true, in the same way. More or less you should be saying more or less the same thing. Okay, the perceived frequency in this case decreases. Okay, right. So, and essentially that is how the cookie crumbles. I thought I would share this question with you. I hope that it helps as you prepare. All right. Otherwise, from me for now, I will see you guys again next time. Sharp, sharp.